Alright, what's up guys? In this video we're going to pick up with some more calculus here, and this is going to be another integration practice video. This is going to be example number 9 of the integration practice series of videos. So we got a definite integral this time. So we got the integral from 0 to 5. We got 2 over x squared minus 4x minus 32 dx. The first thing I always tell students to do is to factor out constants, because sometimes constants can sit in the integrand and make the integral look harder than it actually is. So we'll take it out and deal with it at a later date and time, or later in the problem, I should say. So really what we're looking at is the integral from 0 to 5. Really what we're looking at is the integral from 0 to 5, 1 over x squared minus 4x minus 32, integrated respect to x. So this is a good integral for the method of partial fractions, and that's exactly what we're going to use here. So if you don't know how to do partial fractions or integration using partial fraction decomposition, I got videos on that too, so check that out for a more detailed example. But the first thing that we want to do is we want to factor the denominator here. And remember, to use partial fractions, the degree of the numerator needs to be strictly less than that of the denominator. Can't be bigger than, can't be equal to, needs to be smaller than, which it is, so we're good. And so we need to factor x squared minus 4x minus 32. And what we're looking for is two numbers that multiply together to give you negative 32, but add to give you negative 4. And if I think about that, that's just going to be x plus 4 multiplied by x minus 8. And you can always check that by foiling it to make sure that that's right. You can always check yourself when it comes to factoring things out, or just anything like that, by foiling it. Also, partial fractions is the integration technique that goes back to your use of algebra a lot. So make sure you know how to do things like factoring and stuff like that, because it'll show if you're struggling with that. It'll kind of show here if you don't have that down pat, and you won't have fun with partial fractions. So go back and check that factoring stuff, because it'll come, it's necessary here. So what we do now is just replace this x squared minus 4x minus 32 with that stuff. So this would be x plus 4 multiplied by x minus 8. We now need to find the values of these unknown constants a and b. So now here we'll have x plus 4 plus b over x minus 8. We multiply both sides of this equation here by this denominator, which is x plus 4 multiplied by x minus 8. So we'll do that over here as well, and we'll do that. And so obviously these cancel out over here, so this leaves us with 1 is equal to, well, the x plus 4 cancel out, so this would be a times x minus 8 plus b times x plus 4. All right, so this is where we're at. Now we need the value of a and b. There's two ways you can do this. The easiest way, and the way that students like the most, and it's the way I like the most as well, is substituting in some values of x and try to solve for them, or you, in some more extreme examples of using partial fractions, you need to use or you need to equate coefficients and solve the system. So that's the longer way. Nobody likes doing it that way, but that way is required in some cases. And I do have some videos on where we have to do it that way instead of plugging in values. Luckily for that, using that method really only happens when you have a bunch of unknowns. So in this case, or unknown constants. So in this case, we just got a and b. So, I mean, we could just plug in some values. But once you start getting a, b, c, d, it's just going to be very difficult to substitute in values of x or whatever variables being used to find the values of the unknowns. Equating coefficients and solving this system in that case is probably the best way to do it. But in this case, we really don't have to do any of that. So let's just try to solve for a. So we want to eliminate the other variable. We want to get that other variable to cancel out so that we can solve for a. So what can we let x equal so that we can solve for a? Well, notice if we let x equal negative 4, well, negative 4 plus 4 is 0. B times 0 is 0, so that'll cancel out the b. So what we'll do is we'll let x equal -4. And a common mistake here is students not substituting in the -4 every place you see an x. So not only does it go there, but it also goes there as well. So make sure you plug it everywhere. So we get 1 is equal to a, and put parentheses around negative numbers. That'll decrease the chances of you making a mistake as far as sign changes go. And then it's to be plus b and -4 plus 4. And as you can see here, b just goes away. And we'll simply get 1 is equal to -12a. And if we want to solve for a here, a will simply be equal to -1/12. So that's the value of a. So I'll circle that. And as I talked about in videos that I've done on partial fractions before, the method seems kind of stupid. It's a kind of long, drawn out method, but you know, this is a method that has to be used. And a lot of times you really don't see the benefit of using partial fractions until you've gotten through most of the process. You really don't see the point of it at the first look until you actually get through all of this stuff. And then you probably say, oh, this is what we were trying to do. So, okay, so we now got the value of a, so now we need b. Same process here. We just need to determine the value of x so we can sub in so we can solve for b. And obviously if we let x equal +8, that would cancel out b, or excuse me, cancel out a. So we'll have 1 is equal to a multiplied by 8 minus 8 plus b, and we'll sub 8 in here, so it'll be 8 plus 4, and we'll get 1 is equal to 12b. So that means that b is equal to 1/12. So now we got the value of those unknowns now, those unknown constants a and b. And now this is really when you start to see, let me get another sheet here. This is really now when you start to see the whole point of this whole thing. I'll put it right there. It's just an extra sheet we don't need. Now you really start to see the point of the whole partial fractions thing. So if you remember that the integral that we originally started out with, even after we pulled out I'll just start with what we started with, was the integral from 0 to 5, and it was 2 over x squared minus 4x minus 32. We did pull out the constant, but you get the point. And I just pulled out the 2. So now what we've done is we've taken this integral and turned it into the constant that was pulled out, times the integral from 0 to 5, and it's going to be -1/12 all over x plus 4 integrated with respect to x, plus the integral from 0 to 5, and it was 1/12 all over x minus 8 integrated with respect to x. So what we did was we turned the integral that we could not do immediately into an integral that we now know how to compute, or should know how to compute here. So I mentioned this in the last partial fractions video. Make sure you can compute integrals like 1 over x dx, which is ln absolute value of x plus c, because the vast majority of the integrals, once you've done the whole partial fractions things, obviously there are some exceptions, will yield to these natural logarithms. So you're going to be seeing natural logarithms when you're doing partial fractions a lot. So make sure you know how to compute those. And yeah, so okay, so let's deal with the first one. Let's deal with them one at a time. And that's the best way to do it. So what would the integral of this be? Okay. Well, remember, -1/12 is a constant and can be pulled out. Or imagine that you pulled it out. I know the 2 is out there. We're not dealing with the 2 right now. We'll come back to that. And then that would just leave a 1 on top. So this will obviously be -1/12 ln, and to be absolute value of x plus 4. But we need to evaluate that from 0 to 5. So just think about this integral as an indefinite integral right now. And if you were to take the indefinite integral of this, it would be negative 1 over 12 ln absolute value of x plus 4. And so it would be the same thing. We take the antiderivative. Now we just got to stick the limits on there. Now we plug in the limits. So this will become ln of 9. Remember that ln of 9. Remember ln of 9 is 2 ln of 3. And sticking in the 0 obviously doesn't change anything. So there would be ln of 4. And remember ln of 4 is just 2 ln of 2. So essentially what we would have for this integral here would be negative 1 over 12 multiplied by 2 ln of 3 minus 2 ln of 2 if we use part 2 of the fundamental theorem of calculus. Okay, so that takes care of that one. Now we move to this next one, which is from 0 to 5. And we got positive 1 over 12 x minus 8 integrated with respect to x. All right, so again, that's 1 over 12 ln absolute value x minus 8 from 0 to 5. Okay, absolute value is going to go anyway as well, so just keep that in mind. Now we'll do a little bit of simplifying. So remember, we'll just simply get ln of 3, and then we'll get ln of 8. Remember, ln of 8 can be written as 3 ln of 2. So this would essentially just be positive 1 over 12. And it would be ln of 3 minus 3 ln of 2. So that's what we would get, because ln of 8 is 3 ln of 2. Now you don't have to rewrite things like ln of 8 as 3 ln of 2, or ln of 9 as 2 ln of 3, or ln of 4 as 2 ln of 2. It's just kind of like an extra simplification step. You really don't have to do that. If you just want to leave it as ln of 8, I guess that's fine. I just kind of overdo it a little bit sometimes, maybe. Okay, so now so as you can see, you could do the method of partial fractions with definite integrals too. It's just a bit more of a process when it's with definite integrals than indefinite ones, obviously. So don't forget about the 2 that was out there. Now we just got everything. So we got 2 times negative 1 over 12, 2 ln of 3 minus 2 ln of 2. Or if you wanted to leave it as ln of 9 minus ln of 4, that's fine. Oh, excuse me. This is 2 ln of 2, sorry. And then we'll just add that to positive 1 over 12 ln of 3 minus 3 ln of 2, or ln of 8, however you want to think about it. And now we close it up. And again, all of this came from when we took the partial fraction, got the value of all this stuff, and we computed these integrals here. Now we're just simplifying everything now. We're pretty much almost done with this integral. So let's just simplify all this stuff. First of all, we got our negative out there. Let's just deal with so we got negative 2 ln of 3 minus 2 ln of 2. And perhaps I should have left that in parentheses. I apologize. So what I'll do is since I made an error there, and I'll put it in parentheses just to, and then it'd be ln of 3 minus 3 ln of 2, because that's what ln of 8 was. And then we close all that up. And if we simplify that, we'll get negative ln of 2 minus ln of 3, and that's easily seen there. Now remember that 2 times 1/12, well, or even if it's negative, would reduce down to negative 1 over 6 if we take the negative into account. So since we know that 1 times whatever we get in our numerator after we simplify, which was going to be negative ln of 2 minus ln of 3, we don't have to write 1 over 6. We could just put that all over 6 and give us our answer. So our final answer for this integral here is, first of all, we were asked to integrate from 0 to 5. We were asked to integrate 2 over x squared minus 4x minus 32 with respect to x. All right, so our answer here is going to be negative ln of 2 minus ln of 3 all over 6. That's the answer. You could plug that in a calculator and get like a decimal value for it. I don't know what the decimal value for that is, but you can plug it in a calculator and see what it is. But you can leave it that way if you want. And so that'd be the answer. So I think this was the second example I've done with partial fractions. I don't think I've done very many. So I'll post another video of doing integrals using partial fractions. Just another one of these integration techniques that's helpful. All right. So that's your answer. So let me know if you guys got any questions. I'll see y'all next time.